Let's go back to the material one more time, because we're missing something here. We need to make sure that we don't miss anything. And one important thing we missed in this material so far. So this is the basic material. This is kind of coming from the testing of the prism, concrete prism. And this is coming from the testing of a steel bar. But reality is not concrete prism. Reality is reinforced concrete. So that means they have to be modified somehow. So this is if you compare them together, it's so strange. Look at this stress strain of concrete. It's so small compared to the steel. So it's a really, really weak material in terms of the strain and stress capability. So we somehow have to figure out to improve that. So you can see from there. Now let's come back to this one. We talked about this one, strain and capacity and yield. And then mostly if you load, as everyone has seen this, you load this one, it breaks. But it's interesting how it breaks. It expands horizontally and then disintegrates. So if we did not allow it to expand, it actually won't break. You cannot break a concrete cylinder if you don't allow it to expand because of the Poisson's ratio. So that means this stress strain curve that we got from this one is actually modifiable easily by not allowing this lateral expansion to happen. So if you don't allow it to expand, volume cannot go anywhere. So you can't compress it, you can't crush it. There's nothing you can do. So if you don't allow horizontal expansion, you can't crash concrete. Just like water, the hydraulic or fluid. You push the fluid, it's contained, it's like a jack, it can lift building up because you couldn't compress it. That's the whole idea of a jack that lifts up the building or a car, because you push the liquid and compress it one end, it lifts the building on the other end. So it's the same thing, same concept. So which means we can confine it like this one. So we all know that if we confine it, we make sure it doesn't slip through and we contain it enough, then which means that thing will not break in the traditional way. And that's what happens, that you get that curve. This is the unconfined curve. And if you confine it, you can get that huge big curve, right? We all know that. We have seen that. So that's the way that we can modify the concrete stress strain curve. So this is the stress strain curve. I want to complete this thing. The cycle between the whole analysis that we showed, and to show that we are actually doing it correctly, to prove. So this is the stress strain curve, unconfined. I assign it to a section. Let's say the cylinder become square here, could be cylinder. And then I generate the load deformation curve for this one, axial load, and this one. It looks exactly like this stress strain curve. That means the material stress strain curve is directly leading to the load deformation curve in this particular case with the absence of anything else, right? So that means our correlation between deformation and strain is very much compatible, right? And the stress resultant. So we integrated everything and we got it back. So that means that equation works. Now we have two materials. And not only we have two materials, we have two concretes. One concrete inside the confined zone that we just did, and one concrete outside the confined zone. That means we have to deal with two concretes immediately in the same cross-section plus steel. So concrete, no longer single model can be used. We need to now use two models of concrete, one inside and one outside. This is the model inside and outside plus the steel collect together. But the general procedure remains the same. You add them up again in the same way, integrate them. So this area will be integrated based on this curve, and this area will be integrated based on that curve, right? And then you add them up, and then you can get this is the unconfined plot, this is the confined plot, this is highly confined plot, heavily confined plot. So you can see how we can drastically improve the capacity of a section by confining it and by increasing the confinement from this very brittle material that went over there to a ductile material to a very ductile material, and plus also increase the strength. So this confinement, now we know that we can model it and we can include it in the analysis. Once again, CSI call is used for all these simulations, and then you can get that. And this is how it will look like. Light, no confinement, light confinement, heavy confinement, and very heavy confinement, coming from ETAP CSI detail once again. So you can define these cross sections in the program, and you can get the data from there, and then you can generate corresponding models in CSI call or in section builder, section designer inside ETAPs. Okay. So which means now we are able to add the actual reinforcement effects, both vertical and horizontal, into our analysis that we were doing. But the strength design has no knowledge. If you calculate the moment capacity, it has no effect of the transverse reinforcement. It has, the formula doesn't contain, no matter how many confinements you provide, how many stirrups you provide, the moment capacity is not affected. But in reality, it is affected, and that reality now we can capture. So that's and now we can see here, confined column, unconfined, light, heavy, very heavy. You can actually plot the moment curvature, the strain and that curves. You can plot them all. This is the actual stress strain curve modified by confinement on the same, so you can see the difference between them. This is an arbitrary limit set here. Actually, it could be more, depending upon where, 50, or 60 or something more. So it's not really true. It still could be more. Okay. So still it is 10 times more than unconfined. Unconfined is only 5. Confined is 50 microstrain. So you increase the ductility by 10 times of concrete, which is a brittle material, and so we can now incorporate all of these things into our models. So 2 columns, same axial load, same vertical reinforcement, and different ties can now give you a different moment curvature and capacity. And that's what we are looking for, a reliable way to make that distinction between a school building which provided the confinement and another white that did not provide the confinement. We now have a way to include them in our model and analysis. But still, concrete still is weak. Even after confinement, it's getting better, but still not as good as steel. But of course, it's already 100 megapixel concrete are coming up, so we can have, it's pretty good, but still. All right. Moment curvature curve, the one that we just saw, is affected by so many things. So first of all, the angle on which the curvature is generated, it heavily depends on that, and we often forget that. We are used to looking at the curvature plot on the X or Y. We never often look at them an angle on a biaxial bending, and that you will see is a big challenge. Second one is presence of axial load, because the equilibrium of that equation depends on the axial load. So depending upon how much axial load is, this curve will depend on that. Then of course the confinement and the vertical reinforcement, then the stress strain curves and all, and the cross-section size and shape. So this is going to depend on all of these parameters. That means we have now a very good tool to include all these variations, very specific variations in a structure for which the strength design will give you the same answer. To include them in the investigation, so make the distinction between good and bad and sift them through this way, right? Not just looking at the DC ratio of the moment to decide what to do with it. So that's the advantage, and we use the general equation for all this generation in CSI call for that. And if you look at that now, I rotate the cross section to 45 degrees to see the curvature effects and stress effects. Confined section, outside is confined, unconfined, inside is unconfined. And if we look at that, if you move the cursor around that, you will find the change, and very soon you will find that you're over there, and then the stress, because the corner is now small. Concrete is too small, so it's going to go away very quickly. So you will not get the same moment curvature capacity as on the 0 degree or 90 degree. And then you can see here, the curve, the cover is gone and only core is left. So the cover will be gone very quickly because the corner is under large strain and large stress, and it's unconfined, so it will just go away. So at an angle, the cover will fall and then core will be left, but there is also a triangle. So you don't get a lot of capacity in curvature when you have biaxial bending. Okay, and often we may not see it so clearly. And that's why we have that diagram. That diagram is an interesting plot of moment axial load curvature interaction. So you get the rotation of the cross section plus the axial load plus the maximum curvature, so you can see what will happen. And this is again coming from CSI call. You can see here that this is on the faces, and as soon as you rotate, the capacity, maximum curvature capacity drops significantly because the corner is broken off very rapidly. But as you go up, as the axial capacity, axial load is increased, it doesn't matter so much because now the compression is uniformly distributed. It's not going to make any difference because neutral axis starts at a depth, not at the corner. But for zero moment, neutral axis depth is very small, and then so only corner is under compression, which is gone. So that's why you get this plot. So this plot is quite interesting to see, and this is quite similar to the 3 moment and axial load plots. So one is a capacity plot, moment, axial load, and this is a curvature, rotation angle plus axial load, right? So it is similar. So those two are plotted from the same equations that I showed you using different variation. In this one, the neutral axis angle and the neutral axis depth is varied. In this one, the neutral axis, the cross-section angle, this one also, the angle and the depth is varied for the neutral axis. Here, the angle plus the strain axial load is varied to find the solution that matches with that axial load. Okay, so it's different. So and from both of them, you get very useful information. So from this one, you get PM diagram, the plot between load and moment about any direction. And from this one, that one, and from this one, you get the plot between the moment curvature and the axial load for a given direction of moment. And you also get a plot between 2 bending moments for a given level of P. Because you can cut it horizontally, you get a plot between 2 moments at a given level of P. And here, you get the curvature capacity for a given level of P along the cross-section. So both of them give you a lot of information if you cut them in various directions, right? So this is the advantage of doing all of this work behind, so you get all this information that you can feed back into your evaluation process. Okay, so when you give the SAP or ETABS the fiber section, it generates the moment curvature along each many angles. If you don't give that, you have to give them many moment curvature at different P, at different angles. You need to give maybe 24 multiplied by 5, but 200 or 100 moment curvature curves to complete this plot that I just showed you.